Welcome to Forestry Technology, where raw timber meets precision engineering, and every log tells a story written in steel, data, and discipline. In this episode, we step deep into the modern hardwood industry, a world where forests are not simply harvested, but analyzed, calculated, and transformed with remarkable efficiency. From towering trees in remote landscapes to fully automated sawing lines capable of processing millions of board feet, this is the real journey of wood in the 21st century. The story begins in the forest. Before machines ever touch a log, knowledge comes first. A skilled logger studies the tree, its lean, crown balance, wind direction, slope of terrain. The notch cut is placed deliberately, forming a V-shaped opening that determines the direction of fall. The back cut follows, slightly higher, perfectly horizontal. A wedge is driven in to prevent binding. A hinge is left intact, that narrow strip of fiber that guides the fall with controlled precision. The tree trembles, cracks, and collapses exactly where intended. This is not brute force. This is controlled energy. Extraction depends on terrain. In mountainous regions, cable yarding systems suspend logs across valleys, sliding them through the air toward landing sites. On flatter ground, heavy skidders clamp and drag timber across carefully planned paths that protect soil integrity. Near rivers, floating logs form rafts moved by current, an ancient method still effective today. Where roads allow, reinforced log trucks carry multi-ton loads toward advanced processing facilities. At the mill, raw material becomes engineered product. Inside modern European facilities, automation dominates the workflow. Logs are measured, rotated, scanned, and sorted before the first blade touches wood. Debarkers strip bark with controlled rotational force, revealing clean fiber underneath. Primary breakdown systems bandsaws, circular saws, chipper canners convert round logs into squared cants and sideboards with minimal waste. Advanced 3D scanning and X-ray systems map internal structures invisible to the eye. Knots, density variations, curvature all detected before cutting. Algorithms generate optimal cutting diagrams to maximize yield. Every millimeter matters. Kiln drying follows. Computer-controlled chambers regulate airflow, humidity, and temperature to reduce moisture content to precise targets, often 18% or lower depending on structural requirements. Drying is not just about removing water. It stabilizes the wood, preventing warping and structural failure later in construction. After drying, lumber enters high-speed planing lines operating at extraordinary feed rates. Multiple cutter heads shave microscopic layers, revealing clean surfaces and defined grain patterns. Strength grading technologies such as resonance frequency measurement systems classify boards into structural categories like C24 or C16. Imaging systems detect defects, cracks, color variations, and warp. Decisions once made solely by human eyes are now supported by data-driven evaluation. Yet not all wood is treated the same. In hardwood mills, especially those processing oak, ash, and chestnut, precision becomes even more critical. Hardwood logs carry higher economic value and tighter tolerances. Thin bandsaw blades, sometimes nearly 30 feet long, slice through dense material with minimal kerf loss. Skilled operators still play a decisive role, interpreting grain direction and internal stress before committing to a cut. Manual grading, according to established standards, remains essential in hardwood production. Craftsmen examine color consistency, mineral streaks, knot position, and surface clarity. A minor defect can significantly alter grade classification. Boards are stacked with spacers to ensure airflow during drying, a step that can determine half of the final quality outcome. Across facilities in Scandinavia and North America, the philosophy is consistent: nothing is wasted. In integrated forestry ecosystems, sustainable harvesting is not a marketing slogan, it is operational policy. Logs are traceable. Species are separated and optimized according to structural properties. Douglas fir, spruce, pine, hemlock, each processed on lines calibrated to their mechanical characteristics. What emerges at the end of this chain is not merely lumber. It is engineered material shaped by decades of silviculture, advanced scanning technology, thermal science, mechanical precision, and human judgment. A finished board may look simple. Smooth surface, straight edges, clear grain. But behind that surface lies a complex journey from controlled felling in the forest, to data-driven scanning, to optimized cutting patterns, to kiln stabilization, to strength grading, to automated packaging. It is a chain built on respect. Respect for fiber yield, for structural integrity, for sustainability, and for the forest itself. Forestry technology today is no longer about overpowering nature. It is about understanding it, measuring it, and utilizing it responsibly. Millions of trees continue to grow. Thousands of operators, engineers, technicians, and graders continue refining processes every day. The life cycle of wood keeps turning increasingly efficient, increasingly sustainable, increasingly intelligent. And the next time you touch a hardwood floor, a structural beam, or a piece of furniture, remember this: behind that board stands an entire system of science, machinery, craftsmanship, and discipline. This is Forestry Technology. And the story of wood is far from over.